Now our next video is continue on that same module, module 14, and it takes what we've learned about waves and is now putting it into the context of sound as a wave, right? And so we're going to look at sound. So sound is vibrations traveling through a medium in the form of longitudinal pressure waves. So remember we talked about those waves. And so sound being a longitudinal, it's like the slinky type wave we were talking about. And so you can have the compressions where it squeezes together, and then the spread out, the rarefactions. And so this is what I mean about it being calling a pressure wave. And so when they're squeezed together, lots of high pressure, and then as it spreads out, lower pressure. And the squeeze together, high pressure, and then lower pressure. And so that's how sound is going to be traveling. Now, when you think of sound traveling, sound requires a medium. That means it requires something to travel through. And like I said on the last video, not all waves will need something to travel through. Now, this was experimented all the way back in like the 1600s. I forget, 1660 something, I don't know. Robert Boyle, he was studying this. And what he did is he put well, there's two different stories, but one of the main ones that seems like makes sense, that he put a watch-like clicker thing, like, you know, how they used to have the watches that would hang from the chains, and it was hung in a sealed off glass container. And then with the sealed off glass container, he took a pump and he pumped out all the air. And he had set the watch before all the air was pumped out. He had set the watch to ring and ding like on a little, like the little hammer that would hit the bell. And so it was ringing, but when the air was pumped out, then you could see it continuing to click, 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 but there was no sound. And so the idea that sound actually had to have something to travel through was experimented all the way back in the 1600s. And so then when he added some more air back in, then the sounds slowly would start to come back until all the air was in there. So that's kind of a neat little experiment. They figured that out so long ago. Now with the requiring a medium, it's interesting because when sound propagates out, they always say it's kind of like a bubble. And I put this one of the classes, energy and matter, or matter and energy, they're studying sound too. And I put this, and this was one of their journal notes. I didn't do this one for you guys because, you know, you're high school, so okay. But anyway, so this was my little guy, and you see the little pink dots. The pink dots are the air molecules. So I was trying to illustrate to them as the sound, this is my guy screaming, I guess, or jumping around, whatever. It starts to jiggle, the energy starts to jiggle the molecules, and as it jiggles the molecule, just like the slinky, it squeezes that pressure then hits the next one, and it jiggles this one, and the next one, and jiggles that one, and jiggles that one, and it kind of, they say it kind of balloons out like this invisible bubble around the sound source. And so it's 3D. It's not just like in one direction, and that's why you can hear sounds behind you, from the side. Just depends, you know, obviously, like when I'm running in the morning and I'm talking, if I get ahead of my running partner. Oh wait, who am I kidding? I'm always dragging behind her. Okay, so as she gets ahead of me, she's the fast one, then I'm always trying to talk to her, and sometimes she has to turn back to hear me because of the way the sound is, and vice versa. And so depending on the direction too, you know, but sound is still it's still coming out in all directions and vibrating through the media. So the media is all these little pink dots, and then these blue lines were the ones that were the vibrations, the waves coming out in a bubble. Now again, I didn't do this one, or look, here's the little clock. Look at that beautiful Miss Jody drawing. You ever seen anything so great? See, it's a little hanging there and pumping out. Great. Anyway, I didn't put that one in there for you guys. I gave you a more sophisticated looking diagram for sound. But anyway, all right, so the characteristics for sound are going to be the same characteristics we just talked about. So wavelength, amplitude, frequency, speed. You always have to talk about those four things with waves. So when it comes to sound, though, sometimes things need to kind of be illustrated a little differently, or words might change a little bit, so you have to know which ones relate with what. So wavelength, the length of the wave. We already understand that. And we understand from the calculation that there's a relationship between frequency and wavelength. And I illustrated that in my speaker here. Do you love this speaker here? So here's a speaker, and these lines lines are my sound waves coming out, right? So see how my sound waves, my squishes and whatnot, this is the whole length of a wave. See how they are, there's a larger wavelength between these in a certain amount of time, and then this one over here I'm trying to illustrate. So the lower frequency is going to create a larger wavelength, but a higher frequency, all of these coming out at the same amount of time as this, that would be a higher frequency, will actually create smaller wavelengths. These little waves coming out are representing wavelengths. Okay, so there is that relationship between the wavelength and the frequency. Now amplitude, when you talk about amplitude in sound, what you normally hear is the word intensity. So intensity is the strength of the wave. And so we usually think of it as like the loudness of the wave. So sometimes when you're talking about sound, they don't say, oh, you know, turn up the amplitude. They say, turn up the intensity. That's how much more energy. So, but we got to remember, amplitude is the extent to which the particles are displaced. But this makes sense, the intensity. So they give you an example of the guitar. So you have a guitar string, and as you pull that string, it's gonna vibrate at a certain frequency. But if you pull it really, really hard, you pull it more intense, you're going to create more of a loudness. So that's what's happening here. That's the amplitude. You pull it, you displace that string way up more than when you just pluck at it a little bit, then you're going to have a more intensity. So anytime you hear the word intensity, that's why I kind of search it like that. It's really goes with this category. It's kind of like the new word for the sound category of amplitude. And then the same thing with frequency. Frequency also has a new word that you're going to hear in the sound world. So frequency, the number of waves that pass a given point per unit of time. So if we talk about how many waves are coming at you, the frequency side of things, okay, in sound it's referred to or talked a lot about as pitch. The pitch is really the effect of frequency on the way the human ear perceives it. So it's not that it replaces the word frequency, because it's still about the frequency of the wave, the sound wave, but the way you hear it, it's different, the pitch. Now, when we talk about the frequency sounds, we talked the audible range of what we can hear. So there's lots of frequencies, but there's only a certain area which we can hear, which is called the audible, the sonic side of things. And it's 20 cycles per second. So that means the frequency, how fast it's coming at you, can be 20 cycles per second all the way up to 20,000 cycles per second. That's what we can hear. If we go above that, we can't hear it, but that doesn't mean other creatures can't hear it, because some creatures, their ears are designed to be able to hear higher frequencies where ours aren't. Okay, and I'm going to talk more detail on that on a diagram in a minute. All right, then speed. So speed, again, is S equals D over T, so the distance over time. And so what happens is sound travels at different rates or different speeds through different media. So that's one interesting thing to note, is sound, because it's traveling through something, is going to travel differently through certain things. Like, say, for instance, sound will travel through air at a certain speed, and that's one that we kind of get memorized. I think it's like 331 approximately. I think maybe in our book it does 331.4 or 331. Let me check. So if it goes like 331 something, it's more of a sign of precision. Oh yeah, 331.5 meters per second in our book. But so in air, in dry air, that's going to be the average, okay? But when it travels through water, it travels way faster through water. And so depending on the media, you're going to have different speeds of sound. Okay, so we'll look at that in detail, because we're going to have to learn how to calculate the speeds of sound through different things and different media and different temperatures. Okay, so with this page, or with this topic, we have a diagram page that I'm sending you. And with the diagram page, I have a little diagram of the ear. And I'm also going to be sending you a video on how the ear works, so that you can do this and illustrate, do some notes around about different parts of the ear. Our book only tells us a little bit about this little membrane here, and that is this guy right here, tympanum. This is what in our book calls the tympanic membrane. Also, we refer to that as the eardrum. It's that little stretched over part of membrane that when the waves are coming in, and so if I would be illustrating the sound waves with my marker coming in and they're heading my way, as they're coming in, they're going to be entering this ear canal, and then they're going to be bouncing and eventually hitting that particular membrane, and that's where the vibrations of the membrane, these different parts, which you're going to see on the video and write some more details on them, are going to be what sends the signals as they process the information to the brain. And so sound is only useful, right, if we have this amazingly perfect sensory organ that is going to actually be able to calculate what's happening here and then send those messages to the brain. All right, then on this part of it is just us understanding those two areas of frequency and also amplitude. So frequency, which remember I told you frequency was the new word pitch you'll hear when it goes to frequency. In frequency, we have a couple words that we have to understand. First is I'm going to just circle this one in the middle because it's going to be the middle one, which I already told you. 20 hertz to 20,000 hertz is the audible range. We call it the sonic world. That's what we can hear. But there are frequencies under the sonic world, which is called infrasonic. And so if you go below the audible range, you're going to be infrasonic. And then there's also above that, which is ultrasonic. So you've heard these words before. You're like, oh, it's really ultrasonic, but you don't know what they're talking about. You think it's just a cool word, but no, it's science. So if ultrasonic, like say for instance, they say bats can hear up to 100,000 hertz. So they're way above the 20,000. I don't know if that's, did I write that right? 100,000 or is it 10,000? Some reason that looks funny, but I wouldn't be surprised with bats because they are very, they use all their sound. Well, I'll check on that, and you can check on that in your book too and make sure I got that right. So either 10,000, no, it wouldn't be 10,000, right? Because that would be in that category. So maybe I did get that right. All right, and then cats, they say around 40,000 hertz. They can hear, so way above this sonic world. All right, and then there's also in the amplitude world, which we have the new word intensity, right? So frequency, pitch, amplitude, intensity. There is an intensity, a loudness to sound, and so this loudness to sound was at times can be very dangerous for our ears because too much of that pressure wave hitting that can damage your ears. So there was this scale created, and I gave you a little picture of this little scale, and this is called the decibel scale, if you've ever heard of that, and it's actually really the Bell scale after Alexander Graham Bell. Why they only put one L on there, I don't know, because if it's named after Alexander Graham Bell, then put two L's, but whatever, I'm not going to get into it. But it's called the Bell scale, but really we're used to hearing decibel scale because we use them in a range of decibels. So Alexander Graham Bell, obviously, and an increase in 1 bell corresponds to a 10-fold increase in sound intensity. So as you go up the scale from 0, then you're at 10 decibels, 20 decibels. Well, see, 1 bell, and if we did it in just the bell and not decibel, then that threshold would be 0 to 13 that we would go up here. But since they've created into the decibel, so deci, remember, is 1/10 in the metric unit, so 1/10 of it. So it goes from 0 to 130. So the scale from 0, well, it goes above that, but I'm saying like this is the damaging, from 0 to 130 is some real problems in your ears, okay? So every time you go up, though, it corresponds to a 10-fold increase, the decibel. So you can kind of look and be like, okay, where's the library? Where's my vacuum cleaner? And it's hard to see on this diagram, but it says no risk, negligible risk, a little bit of risk. And then if you come up to this high, it's at risk. And I always like to say, you see where that little iPod is? It's up there in this category because many times we are creating so much sound going into our earbuds that we are getting into a damaging zone. So you don't want too much to be going into this to create the damage, and later on you regret that. So it's very important for you to keep that intensity to a level that is permittable for our particular sensory organs, the ears, that help us with sound. Okay, now with sound, we also have some calculations, and so you'll do a calculation page. Don't forget, just put on a half sheet. And again, what I want you to do is I want you to try these first, then look in the book, okay? So let me see which page these sound ones calculations are. I think it's calculating the speed of sound. Okay, so they are on page 348 and 349. Of course, if you just go along in the book with the videos, but again, don't look at it first. I want you to try it, okay? So what's important about sound is, remember I said sound's going to travel through different media at different speeds. And what they're going to do is they're going to have you calculate it going through air, okay, which I already said was 331.5 meters per second, okay? So, but the thing is with air, the warmer the air gets, the faster it goes. And so you have to keep in mind that as the air gets warmer and it spreads out, then it allows those jumps to be faster, those vibrations to go from molecule to molecule faster. So you have to have a calculation in there that's going to help you calculate the temperature of the air. Okay, so it's going 331 around about in air when it's 0 degrees Celsius. But if you go above 0 degrees Celsius, every 1 degree Celsius it's raised, it goes up 0.6 meters. So what they do is give you this formula to help you to calculate. So you always have to keep the temperature in mind when it's traveling. And the same thing when we start seeing it travel through water and different things. The temperature is going to be important. And so as it's going through the air, how many degrees? This one says if the temperature is 68 degrees Fahrenheit or 20 degrees Celsius, what is the speed of sound? Now, the reason I chose 20 degrees Celsius here is because it works, this 0.6 is in the Celsius because this is a metric calculation. So that way, now if they only give you 68 degrees Fahrenheit, you'd have to convert that into Celsius, but they gave that to you. So what you would do is your speed is 3.31.5 plus your 0.6 multiplied by 20 degrees, because every 1 degree Celsius raised gets another 0.6. So you have to multiply these two. So that's what you would do first, is multiply those two first, and then add these two together to get your calculation of how it's moving, how sound is moving through at that temperature. Okay, and using that same illustration, you do the next one. You see a flash of lightning and then hear a thunderclap. 2 seconds later, the air temperature is 15 degrees Celsius. How far away from, I guess I should say, how far away from you, I don't know why okay, was the lightning formed. So you're going to have to figure out the calculations, then figure out the distance. So you'll have to use that, also the wave equation that we talked about. All right, so do those two and then look at the answers in the book to make sure you got them right. Okay, and again, send me some pictures. I love that. And then this diagram is the second diagram on the sheet that I sent you. And remember, you just cut them right in half. Just fold them in half, lick them, peel them, whatever, or you can keep them together. I can cut them in half too. So this particular diagram helps us understand some more with the sound. And so specifically, this is the understanding of what's called a sonic boom and how it happens when we have these really high-speed jets. So as a jet travels through the air, it produces pressure waves, and which makes sense, right? So it's traveling through, and these waves, which are the longitudinal, the pressure ones, are beginning to bunch up as it starts going and getting faster. Now, if it's under the speed of sound, it's going to be called subsonic. And so subsonic, just like we saw with infrasonic and ultrasonic, in the speed world, it's sub or super. So in the frequency world, it was infra or ultra. And that's the same thing you use with like the speed of light too. You got infrared and ultra red. It's above the visible. So this would be the same sort of thing. With frequency, but with speed, we've got subsonic, below the speed of sound. And then the actual middle one would be the speed of sound, which we would call Mach 1. And that's when we reach that, 331. If it was 0 degrees Celsius, it would be 331.5 or whatever. So it would meet that speed of sound. Now you can get higher than Mach 1. When you get going faster, you can Mach 2, Mach 3. It's 2 times the speed, 3 times the speed, 4 times the speed. The space shuttle is thought at times to be traveling at Mach 10. So that's pretty fast, right? And so, but as you meet that speed of sound, the waves start bunching up. So basically your jet is catching up to how fast the sound is actually moving around it. So it's catching up. It's starting to bunch up. And then once you exceed Mach 1, it outruns the pressure waves. So as it outruns these bunched up, then it starts to create this cone-shaped shock wave and creates what we call the sonic booms. And of course, getting above the speed of sound, you're supersonic. So subsonic under it, Mach, or the regular speed of sound, and then supersonic. But when you do get to this point, then you're creating these big booms. And these big booms are very dangerous. That's why a lot of times the planes don't, or the jets don't go into the supersonic side of things until they're like over the oceans, they say, because it can even, those waves can even damage matter like buildings and stuff. And your ears, of course. And then another thing with sound that we have to note is the Doppler effect. So the Doppler effect is named from Austrian physicist Christian Doppler. And what he realized is that as you are moving, as an object is moving and creating sound, it's got that bunching up situation going on like we've seen there with the sonic boom. And so what happens is, let's say my little car, and he's honking on the horn there. The horn produces sound waves at a constant frequency. So the frequency isn't changing. It's the same amount of waves. But as it moves, it continues to produce the wave. So it's like, you know, it honks the horn, wave, and then it moves up a little bit. Wave, honk, honk, you know, the sound keeps making a wave, and then the car moves up, and the wave, you know, as it's continual. And so they start to bunch up here in the front. And as they bunch up, what you see is you get this shorter wavelength. So the shorter wavelength, see the little lambda there? You'll get a shorter wavelength in the front, and in the back you'll end up having, because they spread out in the back, a longer wavelength. And that longer wavelength in the back, see the little wave there, you're going to have different perspectives from, as you as an observer, depending on where you are listening to this. So if you're the observer here, you're going to hear it differently than if you're an observer over here. And so that's like they say when, you know, the siren on an ambulance is driving by and it sounds differently from when you're here or when you're here. That's all due to the Doppler effect. And so that was the Austrian physicist Christian Doppler. All right, so I think that's the last page for sound. All right, so that's the end of the sound. And actually, other than the experiments, we actually got all of the entire chapter done in that short of a time. So I think that's pretty amazing. The only other thing in the chapter is understanding how to use sound waves. And they talk a little bit about ultrasounds and how those work. And I'm actually sending you a video on that so you can see the ultrasound world, which is super cool. But other than that, we're done. Can you believe it? Wow. A module in 1 week. Look, I'm trying to get back on track there. All right, so keep up the good work, and I'll send you some cool videos on sound, and hopefully we can get back together. I'll send you a little experiment like the one they do in the book, where they take the saran wrap and they stretch it over and put the rice or salt on it, and then they use sound. They bang on a pot or pan or something, and then it makes the sound waves move through, and it moves the matter on the saran wrap. So I'll send you that one, because anybody could do that one at home. You can come up with some contraption, and make sure you take me pictures and send me pictures. Put them in my Dropbox, because I would really love to see that. Okay. All right. I miss all of you guys and hope to see you soon.